The object waiting ahead is unlike anything else in the universe. It has no surface to stand on, no solid structure to crash into, and no light of its own to reveal its presence. It is completely invisible against the darkness of space, yet it can outweigh millions or even billions of stars. Entire galaxies revolve around them. Light itself cannot escape them. They are among the most extreme objects ever discovered, and despite decades of research, they continue to challenge some of our deepest understanding of how the universe works. To understand what is waiting for us, we first have to understand how something so extraordinary can exist in the first place. Every star spends its life fighting a constant battle. Gravity is always trying to pull the star inward, crushing it under its own enormous weight. At the same time, nuclear fusion deep inside its core produces an incredible amount of energy, pushing outward with equal force. For millions or even billions of years, these two forces remain in perfect balance. Gravity pulls inward. Fusion pushes outward. As long as that balance continues, the star remains stable. But no star shines forever. Eventually, every massive star begins to run out of fuel. The nuclear reactions that have supported it for its entire lifetime begin to slow, and the outward pressure weakens. Gravity, which has patiently waited for millions of years, suddenly has nothing left to oppose it. The entire star collapses inward with unimaginable speed. In just a matter of seconds, the core is compressed so violently that temperatures and pressures rise beyond anything we can recreate on Earth. The outer layers explode into space in a brilliant supernova, briefly outshining entire galaxies, while the core continues collapsing under its own weight. Sometimes that collapsing core becomes a neutron star, one of the densest objects in the universe. A single teaspoon of neutron star material would weigh billions of tons. Yet even a neutron star has limits. If the remaining core is massive enough, gravity continues squeezing it beyond every known force in nature. No pressure can stop the collapse. No known material can resist it. The matter is compressed into an incredibly small region, and a black hole is born. It is important to understand that a black hole is not a giant hole floating through space, despite what its name suggests. Nothing has been punched out of the universe. Instead, an enormous amount of mass has simply been compressed into an incredibly tiny volume. The gravity becomes so intense that it changes the very geometry of space and time around it. Rather than pulling objects through space like an invisible vacuum cleaner, a black hole reshapes space-time itself, forcing everything nearby to follow the curves it creates. Around every black hole lies an invisible boundary known as the event horizon. This is often imagined as a physical surface, but it is nothing of the sort. It has no texture, no color, and no material you could touch. Instead, it marks the point where the escape velocity becomes greater than the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary can never return. Not a spacecraft. Not a beam of light. Not even information itself, at least according to classical physics. This is why black holes appear completely black. They are not absorbing darkness. They are simply preventing light from escaping. Any light that crosses the event horizon is trapped forever, making the black hole itself invisible against the surrounding universe. We only know they exist because of what happens around them. Nearby stars orbit invisible objects. Hot gas spirals inward, heating to millions of degrees before disappearing forever. Entire galaxies reveal the presence of supermassive black holes hidden within their centers. Despite their terrifying reputation, black holes are not cosmic vacuum cleaners that wander the galaxy swallowing everything in sight. If our Sun was somehow replaced by a black hole with exactly the same mass, Earth's orbit would remain almost identical. We would continue circling it just as we do today. The only difference is that without sunlight, our planet would quickly become a frozen world. Gravity depends on mass, not on whether that mass is a star or a black hole. Black holes come in different sizes. Stellar black holes form from the deaths of massive stars and typically contain several times the mass of our Sun. Their event horizons may only be a few dozen kilometers across. Supermassive black holes are something entirely different. Found at the centers of most galaxies, they contain millions or even billions of solar masses. The supermassive black hole at the center of the Milky Way, Sagittarius A, contains about 4 million times the mass of the Sun, while some black holes in distant galaxies are thousands of times more massive still. As frightening as they sound, black holes are not rare accidents. They are a natural consequence of gravity itself, predicted by Einstein's theory of general relativity long before any were actually observed. Today, astronomers have found evidence for thousands of them, and they now believe that millions more quietly drift through our galaxy alone. One of those black holes now lies directly ahead of us. At first it appears almost disappointingly small against the vastness of space. But appearances can be deceptive. Every hour brings us closer, and every kilometer we travel draws us deeper into one of the strangest regions the universe has ever created. The real journey is about to begin. Our engines continue pushing us forward as the distance behind us grows almost impossible to imagine. Earth disappeared long ago, followed by the familiar constellations that once filled our night sky. The Sun has faded into just another bright star among billions. Ahead, however, something entirely different dominates the darkness. It does not glow. It does not shine. Yet its presence becomes more obvious with every passing hour. From a great distance, the black hole appears almost empty, like a perfectly circular patch cut out of the universe itself. But as we continue approaching, the surrounding stars begin behaving in ways that seem impossible. Instead of remaining fixed in their positions, they stretch, bend, and curve around the darkness ahead. Entire star fields appear duplicated and distorted. Light that should have traveled in straight lines now follows enormous arcs through space, wrapping itself around the invisible object before finally reaching our eyes. This remarkable effect is known as gravitational lensing, and it is one of the clearest demonstrations that gravity is not simply a force pulling objects together. According to Einstein, massive objects bend the fabric of spacetime itself. Light always travels along the straightest possible path, but when spacetime is curved, even that straight path becomes bent. As a result, the black hole behaves like a giant cosmic lens, warping everything behind it into strange rings, arcs, and distorted images. As we move even closer, another extraordinary feature comes into view. Surrounding the darkness is a brilliant disk of glowing gas, shining brighter than entire galaxies. This is the accretion disk, formed from matter that has been pulled toward the black hole but has not yet crossed the event horizon. Gas and dust race around the black hole at enormous speeds, colliding with one another so violently that temperatures rise into the millions of degrees. The intense heat causes the disk to emit tremendous amounts of visible light, ultraviolet radiation, and powerful X-rays, making it one of the brightest structures in the universe despite orbiting one of its darkest objects. The disk itself presents another strange illusion. Instead of appearing as a simple flat ring, portions of it seem to float above and below the black hole at the same time. This is not because the disk is twisted. Once again, gravity bends the paths of light, allowing us to see light from the far side of the disk carried over the top of the black hole before reaching our spacecraft. The result is an image so unusual that it almost appears computer-generated, yet it is exactly what Einstein's equations predict. As our velocity increases, the view continues changing. The stars ahead seem brighter, while those behind begin fading. Light itself shifts in color depending on its direction of travel, an effect caused by our tremendous speed combined with the intense gravity surrounding the black hole. The universe begins losing the familiar appearance it has held for billions of years. Straight lines no longer appear straight. Distances become increasingly deceptive. Every glance out the window reminds us that we are entering a region where everyday intuition simply no longer applies. The closer we travel, the larger the black hole appears. Yet no matter how carefully we observe, we still cannot see the event horizon itself. There is no glowing boundary waiting ahead, no visible wall separating safety from danger. The point of no return remains completely invisible, hidden only within the mathematics describing gravity itself. Even now, while we are still safely outside the event horizon, something much more subtle has already begun. Our clocks continue ticking normally. Our heartbeat feels unchanged. Every system aboard the spacecraft appears to function exactly as expected. Yet to someone watching from a safe distance far away, our journey is beginning to unfold very differently. We have not yet reached the black hole. But time already has. As your spacecraft continues its silent descent toward the black hole, nothing inside the cabin seems unusual. The engines hum steadily. The instruments function normally. Your heartbeat remains calm. Every second on your clock passes exactly as it always has. If you had no window to look through, you might believe that nothing at all had changed. Yet somewhere far away, someone watching your journey from Earth would witness something entirely different. One of the greatest discoveries in modern physics is that time does not pass at the same rate everywhere in the universe. We often imagine time as a universal clock, ticking at exactly the same speed for every person, every planet, and every galaxy. But Einstein showed us that this comforting idea is an illusion. Time is flexible. It can stretch. It can slow down. And gravity is one of the forces capable of changing its flow. The stronger the gravitational field, the more slowly time passes. This is not simply a theory or a mathematical curiosity. It has been measured countless times. Atomic clocks placed on mountaintops tick slightly faster than identical clocks at sea level because they experience slightly weaker gravity. The difference is incredibly small, but it is real. Even the satellites that make the global positioning system possible must constantly correct for this effect. Without accounting for Einstein's equations, GPS would accumulate errors of several kilometers every single day. The technology we rely on to navigate our world works only because time itself does not flow equally everywhere. Near a black hole, however, this familiar effect becomes unimaginably more powerful. As gravity grows stronger, every process aboard your spacecraft begins slowing relative to the outside universe. Your heart beats more slowly. Your thoughts occur more slowly. Light emitted from your ship loses energy as it struggles to climb away from the immense gravity, shifting toward longer and redder wavelengths. None of this is noticeable to you because everything around you slows together. Your clock, your body, your computer systems, and your perception all remain perfectly synchronized. But imagine someone observing your spacecraft from a safe distance. Through a powerful telescope, they watch you continue approaching the event horizon. At first, everything appears normal. Then your movement begins to slow? Not because your engines have failed, but because your time itself is passing more slowly compared to theirs. The closer you come to the black hole, the slower you appear to move. Your radio transmissions become increasingly stretched apart. Your voice grows deeper and lower in pitch until eventually it fades beyond detection. To that distant observer, you never quite reach the event horizon. Your spacecraft appears to freeze just above it, moving more slowly with every passing moment but never actually crossing the boundary. As the light escaping your ship becomes increasingly redshifted, you gradually fade from view until you become invisible altogether. From their perspective, you simply disappear. Yet inside the spacecraft, your experience could not be more different. You notice no freezing, no slowing, no mysterious force holding you back. Your clocks continue ticking normally. Your conversations proceed naturally. You continue moving steadily toward the black hole, unaware that the outside universe has begun racing forward without you. This creates one of the strangest situations in all of physics. Two observers witness the same event, yet they describe completely different realities. One insists that you never cross the event horizon. The other experiences crossing it in finite time. Remarkably, neither observer is mistaken. Both descriptions are correct because time itself is no longer absolute. Each observer measures reality according to their own path through spacetime. As the minutes pass aboard your spacecraft, years may already be passing for distant civilizations. Continue the journey a little longer, and decades unfold elsewhere. Continue farther still, and entire centuries may pass while only hours elapse for you. Civilizations could rise and fall. Languages could evolve beyond recognition. The descendants of everyone who ever knew you might look back at your mission as ancient history, while for you, the launch from Earth still feels surprisingly recent. The closer you drift toward the event horizon, the more dramatic this difference becomes. The universe outside seems to accelerate. Light arriving from distant stars carries information from further and further into the future. Galaxies continue their slow dance across the cosmos while you descend into a place where time itself is losing its familiar meaning. Soon, there will no longer be any disagreement about what happens next. The event horizon is waiting only moments ahead. For generations, artists and filmmakers have imagined the event horizon as a dramatic barrier, an invisible wall separating the ordinary universe from the unknown. Some portray it as a glowing sphere. Others imagine violent explosions, crushing shockwaves, or mysterious energy fields that destroy anything attempting to pass through. It is an understandable image, but according to everything modern physics tells us, it is almost certainly wrong. As your spacecraft continues its descent, there is no visible line stretched across space. No warning lights suddenly activate. No alarm announces that you have reached the point of no return. The stars remain visible outside your window. The instruments continue operating exactly as before. Your engines respond normally. Every physical process aboard the spacecraft appears completely unchanged. Then, without realizing it, you cross the event horizon. Nothing happens. There is no impact. No sudden jolt. No flash of light. If you were not carrying an extraordinarily accurate map of spacetime, you would never know the crossing had already occurred. This surprises many people because we naturally expect such an important boundary to announce itself. Yet the event horizon is not a physical object. It is not made of matter or energy. It is simply a location where the geometry of spacetime changes in a profound and irreversible way. Outside the event horizon, there are still paths that lead away from the black hole. Your engines may not be powerful enough to follow them, but in principle those escape routes still exist. Inside the event horizon, those possibilities disappear forever. Every future path through spacetime points deeper toward the center. Escaping is no longer difficult. It has become physically impossible. To understand why, imagine standing on the side of a mountain. No matter which direction you choose, there is always at least one route leading uphill and another leading downward. Inside the event horizon, it is as though the landscape itself has changed. Every possible road now slopes toward the same destination. Turning around no longer helps because every direction leads inward. Even a beam of light, the fastest thing in the universe, finds every possible path carrying it closer to the center rather than farther away. This is why scientists often say that crossing the event horizon is less like entering a place and more like entering a new region of spacetime where the ordinary meaning of direction begins to fail. Concepts that have guided every moment of your life, forward, backward, escape, return, no longer describe reality in the way they once did. Meanwhile, the universe outside continues transforming before your eyes. Because of the enormous gravitational distortion surrounding the black hole, light arriving from the distant cosmos carries information from increasingly far into the future. Depending on the size and rotation of the black hole, you may witness stars aging, galaxies slowly changing their positions, and vast stretches of cosmic history unfolding at extraordinary speed. The universe you left behind is no longer progressing alongside you. It is racing ahead. Yet there is one thing you will never witness. You will never see yourself leave. Every beam of light you emit after crossing the event horizon remains trapped with you. Every radio message, every photograph, every signal generated by your spacecraft is now confined forever inside the black hole. Communication with the outside universe has ended without either side ever hearing a final goodbye. Behind you lies everything that has ever existed in your life. Earth. The Sun. The Milky Way. Every person who has ever lived. Every memory you have ever made. They still exist, but they have become forever unreachable. The event horizon has not destroyed them. It has simply placed them beyond a boundary that no signal, no spacecraft, and no law of physics currently allows you to cross again. Ahead lies only one destination. The gravity that has guided your journey from the very beginning is becoming stronger with every passing second, and soon its effects will no longer remain invisible. The true violence of the black hole is only just beginning. Until now, the black hole has behaved with surprising subtlety. Time slowed? Light bent. The universe distorted around you in extraordinary ways, yet your spacecraft remained intact. There were no violent impacts and no invisible walls waiting at the event horizon. For a while, it almost seemed as though the greatest danger of the black hole had been exaggerated. That illusion cannot last forever. Gravity is often described as a single force pulling equally on everything around it, but this is only approximately true. In reality, gravity becomes weaker with distance. Here on Earth, the difference between the gravitational pull on your head and your feet is so tiny that you never notice it. Our planet is simply too large and its gravity too gentle for the effect to matter. Near a black hole, however, gravity changes so rapidly over relatively short distances that different parts of your body no longer experience the same pull. Imagine floating feet first toward the center of the black hole. Your feet are slightly closer than your head, perhaps by less than 2 meters, yet that tiny difference is enough. Gravity grips your feet more strongly than your head, pulling them inward with greater force. At the same time, the sides of your body are squeezed inward while your length is stretched farther and farther along the direction of the gravitational field. These unequal forces are known as tidal forces, and they become the defining feature of the final stages of your journey. At first the effect is almost impossible to detect. Sensitive instruments aboard your spacecraft register tiny differences in acceleration between its front and rear sections. The structure begins compensating automatically, distributing stress across its frame just as engineers designed it to do. For a brief time, nothing appears unusual. But every second carries you deeper into a region where gravity grows dramatically stronger. The differences measured by the instruments increase rapidly until even the strongest materials ever built can no longer withstand the strain. Long before your spacecraft reaches the center, its structure begins to fail. Bolts experience forces they were never designed to resist. Support beams twist under enormous stress. One section after another starts tearing apart, each fragment following a slightly different path toward the black hole. The spacecraft that carried you across interstellar space slowly loses its battle against the immense curvature of spacetime. If no spacecraft surrounded you, the same process would occur to your own body. Every cell, every bone, every organ would experience slightly different gravitational forces. The stretching would continue relentlessly while compression from the sides became increasingly intense, gradually transforming your body into an impossibly long, thin stream of matter. Physicists sometimes refer to this process with an unusual name, spaghettification. The word sounds almost humorous, but the phenomenon itself is among the most violent consequences of gravity anywhere in the universe. Surprisingly, this fate depends greatly on the size of the black hole. It seems reasonable to imagine that larger black holes are always more dangerous, yet the opposite is often true. A small stellar black hole, containing perhaps 10 times the mass of our Sun, has an event horizon only a few dozen kilometers across. Its gravity changes so rapidly that the tidal forces near the horizon are already catastrophic. Anyone approaching such a black hole would almost certainly be torn apart before or just as they crossed the event horizon, never experiencing what lies beyond. A supermassive black hole tells a very different story. Although it contains millions or even billions of times more mass, its event horizon is enormously larger. Because of that vast size, gravity changes much more gradually across the length of a human body. The difference between your head and your feet at the moment you cross the horizon may be surprisingly small. In theory, you might pass through the event horizon of a supermassive black hole without feeling anything unusual at all. But gravity never stops increasing. As you continue falling inward, the tidal forces grow stronger with every passing second. Eventually they become overwhelming regardless of the black hole's size. The only difference is where it happens. A stellar black hole destroys you before the horizon. A supermassive black hole may allow you to survive the crossing, only to meet the same unavoidable fate much deeper inside. By now, there is no longer any possibility of escape. Your spacecraft is gone. The familiar universe has disappeared behind you. Every future moment carries you farther inward, toward a destination from which neither matter nor light has ever returned. And inside the black hole, reality itself is about to become even stranger. Everything you have experienced so far has still belonged to a universe that physicists believe they understand. Einstein's theory of general relativity has accurately described every stage of your journey, from the bending of light to the slowing of time and the immense tidal forces stretching everything toward the center. Yet now you have entered a region where even these remarkable equations begin revealing a reality unlike anything encountered anywhere else in the cosmos. The first thing to understand is that there is no empty chamber hidden inside the black hole. Popular illustrations often depict enormous hollow spaces, mysterious tunnels, or vast underground caverns concealed beyond the event horizon. According to general relativity, none of these images are correct. A black hole is not a giant empty container waiting to be explored. Instead, it is a region where the geometry of spacetime has become so severely distorted that our ordinary understanding of movement begins to fail completely. Outside the event horizon, you are free to choose your direction. You can walk north or south. A spacecraft can accelerate left, right, upward, or downward. Every moment presents countless possible paths through space. Inside the event horizon, however, those choices become increasingly meaningless. No matter how you fire your engines, no matter which direction you attempt to travel, every possible future carries you closer to the center. An unusual comparison may help illustrate this idea. Right now, as you sit watching this video, you are traveling through time whether you choose to or not. You cannot decide to remain in yesterday, nor can you steer yourself toward next week more quickly than 1 second at a time. The flow of time is unavoidable. It constantly carries you forward without asking your permission. According to Einstein's equations, something remarkably similar happens inside a black hole. Falling toward the center becomes as inevitable as moving into tomorrow. It is no longer simply a direction through space. It becomes part of your future itself. This is why escaping from inside the event horizon is fundamentally different from escaping a powerful gravitational field elsewhere in the universe. A rocket leaving Earth can always overcome gravity by producing enough thrust. A spacecraft leaving the surface of a neutron star could do the same if it possessed sufficient energy. Inside a black hole, there is no amount of thrust that changes your destiny because there is no future in which you move outward. Every physically possible path through space-time points inward. Trying to escape is no more meaningful than trying to travel backward through time. As you continue your descent, the remaining light from the outside universe grows increasingly distorted. The stars that once surrounded your journey have disappeared. Signals from distant galaxies can no longer reach you in the familiar way. Whatever lies beyond the event horizon has become permanently separated from your experience. From this point forward, the only reality you can observe exists entirely within the black hole itself. What happens next depends on details that physicists are still struggling to understand. General relativity predicts that every path eventually leads to a single destination known as the singularity, a place where the curvature of space-time grows without limit. Yet many scientists believe this prediction signals not a real physical object, but the point where our current theories begin to break down. Whenever equations produce infinities, history has repeatedly shown that nature is usually telling us something important is still missing. This is the frontier where two of the greatest achievements in modern physics collide. General relativity describes gravity with extraordinary precision across the largest scales in the universe. Quantum mechanics explains the strange behavior of matter and energy on the smallest scales imaginable. Both theories have passed every experimental test ever placed before them, yet inside a black hole they refuse to fit together. Each appears incomplete without the other, leaving physicists searching for a deeper theory capable of uniting them. For now, your journey has carried you to the very edge of human knowledge. Everything behind you can be described by equations tested across the universe. Everything ahead lies hidden behind mathematics that no longer agrees with itself. And waiting at the center is the greatest mystery of them all. The singularity. Every path through the black hole has been leading toward a single destination. According to Einstein's theory of general relativity, nothing can prevent it. Whether you fall freely, fire your engines, or simply drift with gravity, every possible future eventually converges on the same point. Physicists call this destination the singularity, a place where our current understanding of the universe reaches its absolute limit. At first glance, the idea seems almost impossible to accept. The equations of general relativity predict that matter collapsing under its own gravity can be compressed into an infinitely small point with infinite density and infinite curvature of space-time. These infinities are not merely unimaginably large numbers. They are mathematical signals that something has gone fundamentally wrong. Nature has repeatedly taught us that whenever our equations produce infinities, they are usually revealing the limits of the theory itself rather than describing physical reality. This has happened before. Early theories of electromagnetism predicted infinite energies under certain conditions until quantum mechanics provided a deeper explanation. Classical physics failed to describe atoms until an entirely new framework emerged. In much the same way, many physicists believe the singularity is not an actual object waiting at the center of every black hole, but rather evidence that general relativity is incomplete when gravity becomes overwhelmingly strong. The problem becomes even more fascinating when quantum mechanics enters the picture. Quantum theory tells us that information about the state of a physical system cannot simply disappear. Every interaction, every particle, every quantum state contributes to a complete description of reality. In principle, the history of the universe is always encoded within its present state. Information may become scrambled beyond recognition, but it should never be destroyed. Black holes appear to violate this rule. Imagine placing a library inside a spacecraft and allowing it to fall through the event horizon. Every book, every photograph, every computer file, every record of human history disappears behind the horizon along with it. If the black hole eventually evaporates through a process known as Hawking radiation, what becomes of all that information? Has it vanished forever? Or is it somehow hidden within the radiation escaping the black hole over unimaginable spans of time? This question became one of the greatest scientific debates of the 20th century. In the 1970s, Stephen Hawking showed that black holes are not completely black after all. Quantum effects near the event horizon allow them to emit an incredibly faint form of thermal radiation. Over periods vastly longer than the current age of the universe, this process would slowly cause black holes to lose mass and eventually disappear entirely. At first, Hawking argued that the information carried into the black hole would be permanently lost. If true, one of the most fundamental principles of quantum mechanics would be broken. Many physicists found this conclusion deeply troubling. If information can truly vanish from the universe, then the predictability of quantum physics itself begins to unravel. Decades of research followed, producing countless new ideas but no universally accepted answer. Eventually, Hawking himself changed his position, suggesting that information may not be destroyed after all, although exactly how it escapes remains uncertain. Among the proposed solutions is a remarkable idea known as the holographic principle. It suggests that everything falling into a black hole may somehow be encoded on its event horizon, much like a three-dimensional image can be stored on a two-dimensional hologram. If this idea is correct, the event horizon is far more than an invisible boundary. It may function as a vast cosmic archive, preserving every piece of information that has ever crossed it. Another proposal is even more startling. Some physicists have suggested the existence of a firewall, an immensely energetic barrier located precisely at the event horizon. Instead of passing through unnoticed, as general relativity predicts, anything crossing the horizon would be instantly destroyed. This idea attempts to preserve quantum mechanics, but it comes at the cost of overturning Einstein's prediction that crossing the horizon should feel completely ordinary. Once again, two of our greatest theories refuse to agree. After decades of research, the debate continues. Some theories preserve general relativity. Others preserve quantum mechanics. Others attempt to replace both with an entirely new understanding of reality. None has yet been confirmed. Standing at the edge of this mystery, one thing becomes clear. Black holes are not merely astronomical objects hidden among the stars. They have become laboratories where the deepest laws of nature confront one another. Every unanswered question surrounding them may ultimately reveal an entirely new layer of the universe itself. And that raises one final possibility. What if a black hole is not the end of the journey at all? Throughout this journey we have remained as close as possible to established science. Every stage, from the birth of black holes to gravitational lensing, time dilation, tidal forces, and the event horizon, has been supported by decades of observation and the remarkable success of Einstein's theory of general relativity. But once we venture beyond that foundation, we enter a landscape where scientific investigation meets informed speculation. Here, the questions become even more extraordinary than the answers. One of the oldest ideas is that black holes might be connected to another region of spacetime through structures known as wormholes. First proposed as mathematical solutions to Einstein's equations, wormholes are often imagined as shortcuts connecting distant parts of the universe. Instead of traveling across billions of light years, a traveler could theoretically pass through a tunnel linking two otherwise unreachable locations. In popular science fiction, wormholes have become familiar gateways across space and time. In reality, however, no evidence has ever confirmed that such structures exist in nature. Even if wormholes are mathematically possible, they present enormous challenges. Most solutions suggest they would collapse almost instantly unless held open by an exotic form of matter possessing negative energy, something that has never been observed in the quantities required. While quantum physics allows tiny amounts of negative energy under certain conditions, whether enough could exist to stabilize a traversable wormhole remains entirely unknown. Closely related to this idea is the concept of a white hole. If a black hole allows matter to enter but never leave, a white hole would behave in precisely the opposite way. Matter and energy could emerge from it, but nothing would ever be able to enter. Some theoretical models treat black holes and white holes as two ends of the same spacetime structure, although no white hole has ever been observed anywhere in the universe. At present, they remain intriguing mathematical possibilities rather than established physical objects. Another fascinating possibility emerges when the black hole itself is rotating. Most real black holes almost certainly spin, because the stars that formed them were already rotating before they collapsed. These rotating solutions, known as Kerr black holes, possess a far more complicated internal structure than non-rotating black holes. Certain mathematical descriptions even suggest pathways that avoid the central singularity entirely, leading instead to other regions of spacetime. While these solutions are beautiful on paper, most physicists suspect that real black holes would become unstable long before such journeys could ever occur. Some theories go even further, suggesting that black holes may have played a role in creating entirely new universes. In these models, the immense gravitational collapse inside a black hole could trigger the birth of a new expanding cosmos disconnected from our own. If such ideas are correct, every black hole might contain a universe invisible to its parent, while our own universe could itself have originated inside a black hole existing within another, older cosmos. It is an astonishing possibility, but one that currently remains beyond observational testing. The search for answers has inspired some of the most ambitious efforts in modern theoretical physics. String theory proposes that the fundamental building blocks of reality are not point-like particles but unimaginably tiny vibrating strings existing within additional dimensions of space. Loop quantum gravity takes a different approach, suggesting that space itself is woven from discrete quantum units rather than being infinitely smooth. Although these theories disagree on many details, both attempt to solve the same profound problem: how to unite general relativity with quantum mechanics and explain what truly happens where our current equations fail. For now, however, the honest answer is remarkably simple. We do not know. No spacecraft has ever crossed the event horizon and returned. No telescope can observe what lies beyond it. Every prediction about the interior of a black hole comes from mathematics, carefully tested theories, and the relentless effort of scientists trying to understand a universe that often refuses to reveal its secrets. Some ideas may one day prove correct. Others will almost certainly be discarded. That is how science has always advanced. Our journey began on Earth with a simple question. What would happen if you fell into a black hole? Along the way, we discovered that the answer is far stranger than anyone imagined. Gravity bends light until the universe appears distorted. Time itself flows differently for different observers. The event horizon is not a physical barrier but a boundary in spacetime. The immense tidal forces inside the black hole can tear matter apart, while the singularity exposes the limits of everything modern physics currently understands. Yet perhaps the greatest discovery is not what we have learned, but what we still do not know. Black holes remind us that even after centuries of scientific progress, the universe continues to hold mysteries beyond our reach. They stand as silent guardians at the frontier of human knowledge, where observation ends, mathematics begins, and imagination is guided by evidence but never allowed to replace it. Perhaps one day, a new theory of physics will finally reveal what truly lies beyond the event horizon. Or perhaps some mysteries are destined to remain forever hidden from every civilization that has ever looked toward the stars. Until that day comes, the journey ends here. But the mystery of the black hole has only just begun.